Continuing with some of the lower level design tools, we're still talking about place and route, and these are definitely common design tools in the synthesis process. And primarily here we're going to be talking about the place and route tools, which would be for the place and routing of cells. So they're used primarily with standard cell design methodology or gate arrays or FPGAs. Design descriptions would be expressed perhaps as a sea of gates all connected together. And that name basically is for a technology which was known as gate arrays, and it's reasonably deprecated at this point in time. But in any event, each gate or cell would typically be a common combination logic operation or a sequential gate, a latch or a flip-flop. And an FPGA, which is much more modern technology, would typically be a lookup table, or maybe you'd see the word LUT. So place and route tools, the layout of the gates and cells are already available in a library. Typically the cells are pre-made, and you're interested in placing the cells in a design and then routing the connections. So placement and routing tools ideally would work together because selection of placement and routing algorithms do depend on one another, and it would be desirable if in fact they could communicate back and forth to some degree. That's not often the case. More typically you might find a placement stage followed by routing, and if it doesn't meet the specification, that would be redone. Placement is one of the hardest problems to solve in an effective manner, and you might ask yourself why that be the case, and we'll discuss that in a minute. But anyway, the purpose of placement tools or floor planners is to place blocks in a design in such a manner that the routing tools connect the proper ports together. And again, you want to do that probably minimizing something like wire area or overall area. So this problem is known to be NP complete, so that means non-deterministic polynomial time complete, and very likely the complexity increases exponentially with the problem size. So the point here, it's very difficult types of problems to solve optimally. So as a result, none of the algorithms that are commonly used are truly optimal, but designers are not necessarily interested in optimal design. You basically want a design that would meet the design specifications. In the case of a layout, you may have additional constraints, such as the design must occupy a given area and meet some timing requirements. And in any case, probably you should note that constraints make things more difficult, not less. One of the simplest algorithms used in placement is the min-cut algorithm, and we'll discuss that briefly, but the idea is to partition the design recursively into two equal halves, and each time you do that, you try to minimize the number of wires connecting the two components. So each partition is made so the minimum number of connections cross-partition. So you might end up with a reasonable circuit if you use this technique. So they're going to look at an example here in a minute, and basically it shows the blocks in a design. The number of connections between the blocks is represented by the connection line thickness. So the thicker the line, the more connections. And then the second part of the figure will show the final placement with the cut lines. A vertical cut line was made first, and it was followed by two horizontal lines, which represent the second set of cuts. So this allows the design to be placed while emphasizing reducing the total wire area and reducing bottlenecks associated with congestion that you might otherwise have if you have a highly routed area. So this results in a higher performance design and one which consumes less area. Those typically go hand in hand with one another. So this is that figure here shown before. You have a layout. These are just arbitrarily placed at this point in time, and then you go through two phases of min-cut algorithm with cutting the design into two sides and then cutting those further into two sides as well, or top and bottom. And there's an example where the final places should be. So really what you want to get them is semantically correct, and that means where they should be in relation to one another. The difficulty comes when partitioning components into two roughly equal sized number of components. If you didn't have this constraint, this problem is not nearly as hard. It really isn't even in the class NPC anymore, and it would be solvable with a maximum flow type algorithm. So it's a funny kind of problem in that it has a large number of solutions, many of which are acceptable but not likely optimal. The original paper that sort of outlined much of this type of problem for non-deterministic algorithms was Kirkpatrick in about '83, and he denoted that problem analogous to an Ising spin glass, which means there's a whole bunch of low energy solutions, but not necessarily global minima. So it makes it very reasonable to tackle. That's what that basically means. There's a lot of acceptable solutions. This is a little introduction by Kang et al. From a Springer Verlag publication 2011, and it just goes over the placement parts a little bit here. So here's an example of placement. Here's a circuit that we're familiar with seeing. It's a schematic representation of it, and over here it sort of shows a linear placement, and over here shows a 2D kind of placement. And this final figure just sort of shows the cells which are placed and then routed together, as well as VDD and ground. So this would have been placement and routing with standard cells. So placement part, and then complete with the routing as well. So there's obviously going to be a trade-off in good versus bad placement. Here's an example of bad placement. It causes routing congestion, which results in increased circuit area or cost in wiring. And the longer wires will imply more capacitance. As a consequence, we get longer delay and higher dynamic power dissipation. If we go back to any of our equations related to power dissipation, we'd see that. A good placement, on the other hand, the circuit area and the cost and the wiring would decrease, and the shorter wires would lead to less capacitance, shorter delay, less dynamic power dissipation. So here's an example of two different types of partitions, or two different partitions rather, for that circuit that we showed previously. And one was sort of cut A and the other was cut B, and it sort of shows in one case you have fewer wires than the other. So somewhat obvious that the placement is going to be dependent upon where you make those cuts. And just one other thing to point out, people working on these types of problems, it's basically graph type problems. So you talk about nodes, vertices, and cut sets. Here's the Kernighan-Lin algorithm. It's fairly old, from I think the early 70s. And basically you're given a graph with two end nodes where each node is the same weight, so basically the same size in that case. And the goal would be to partition this design into two disjoint subsets, A and B, with a minimum cost between the two. So you put some nodes on one side, some nodes on the other, and the cost is the number of wires which connect up these two blocks. This part here, by the way, where you're constraining A to these are cardinality, the size of the set A and the size of the set B both equal to n, makes the problem very difficult. If that wasn't the case, like I said before, it would be quite an easy problem to solve. Put them all on one side. Anyway, here's some of the basic concepts. You associate a cost with moving a node. So this sort of associates the cost as being the number of incident edges which are cut by the cut line, and the number of edges that are not cut by the cut line. So a high cost means that you should probably move that node. A low cost probably means that that node should stay in the partition that it's in. And there's just a couple of examples of it over on the right hand side. So there's also something defined here as the gain of swapping a pair of nodes A and B. So it's the gain is going to be the cost of A plus the cost of B minus 2 times the cost of AB. Otherwise, the 2 is in there because you'd be counting them twice. So this gain indicates how useful the swap would be between the two nodes. The larger delta G, the more the total cost will be reduced. So basically you want to try to reduce that total cost. So that algorithm works as follows: by picking pairs to swap, and you pick those pairs as being the pairs which give you the most gain. And you can go through this on your own as you like, and you can sort of see if you pick those two that are illustrated here, you'll go from a cut of 9 to a cut of 8. And here's this another example where it was node 5 and node 3 were selected. So you typically will pick the pair of nodes which give you the greatest gain, or the greatest reduction in the number of wires crossing the partition. And so here's it sort of shows the algorithm working, and it plugs away along keeping partitioning the design until you end up with a minimum number of cuts across here, and further swappings would increase the cost. So you basically, it's like a greedy algorithm. You end up with a reasonably useful solution. And this sort of illustrates the delta G's here were positive, and after that point in time the delta G's were negative, so the gains were getting negative, and here the gains are positive. So reducing the cost, increasing the cost from here on in. This is the only part that seems a bit questionable from these notes. It sort of said since this G of M was greater than 0, more passes are needed until G of M is less than 0. But at any point, they probably meant we're referring to the delta G. Because in this case, if you find a delta G that's positive, you'll end up reducing the cost, and if the delta G is negative, you'll end up increasing the cost. In any event, this is done recursively, so the first pass would have partitioned it into these two sets of elements, and then the next time you partition these, and you partition these again. So anyway, back to maybe something a little closer related to chip technology. We'll look at some standard cell row placement. Standard cell methodology just means that you're trying to place cells that have been predefined, and you have some simplified knowledge of the cell structure. But typically, you know where the ports are and what the cell is and the power and ground. So cells can be abutted to one another in this fashion without causing a design rule violation. Placement of standard cells could be implemented. The cells in a row, separated by channels, would be used for routing. This again is a little bit deprecated, and we'll see that why that be the case in a minute or two. So a min-cut algorithm or other techniques such as simulated annealing would still be employed to determine the position of the cells in the rows. The rows of cells may also contain some feed-through cells, which would disallow connectivity between the rows of cells. So one of the questions might be, what would a feed-through cell look like? Well, hopefully it looks like a wire that you can connect from the top and the bottom. And this need is mitigated by multiple metal layers that you have nowadays, as well as probably all the wiring that would have been previously done in a routing channel. So here's an example of what an integrated circuit would look like with standard cells and space for routing. Standard cells followed by space for routing. So one of the in-class assignments would be what are in the cells. I'm going to talk briefly about simulated annealing. The complexity of placement algorithms make algorithms such as simulated annealing very attractive alternatives. The downside is they do require plenty of CPU time, but it certainly is a workhorse algorithm which mimics the annealing of a liquid or solid. Others algorithms are used, but simulated annealing is certainly one that you should be aware of and be somewhat familiar with. It's very appealing, very intuitive, and straightforward to implement. That's the nice thing about it. The hard part is, and the engineering part, and the part that you have to work hard to make sure it's working perfectly, is that you need a really good cost function. And the cost function is basically what you're trying to optimize. So this is where the engineering intuition comes from, and the experience and everything else you'd use to try to improve your design, coming up with a good cost function and probably reasonable control parameters that you might have to tweak with this type of algorithm. But this is the idea behind it. Again, it's taken from the same reference there. This is sort of shows the cost function over time, and what you're hoping is, in this case, you're trying to minimize costs, and you're going to plateau out to something which is going to meet your specification. And the way this happens is it basically will swap a couple of components, and if that new swap means that it's going to be a better placement, then you'd keep it. If it doesn't improve it, you probabilistically will keep that, and that'll be related to a temperature-dependent probability or control parameter probability. Here's a little bit of pseudocode for it. So you set up an initial temperature or control parameter. You have an arbitrary initial placement. That's a nice thing. It's very easy to do. And what you do is you keep basically running the algorithm at the same control parameter a number of times until you come to equilibrium, and that sort of means the design isn't changing much, at which point in time then you would reduce the control parameter. So a couple things will happen. You'll take a new solution. It's just the perturbed version of the previous solution. Calculate the changing cost. If the cost went down, you accept it as the current solution, and if it isn't, you select it probabilistically. And once you've done this enough times that you're in equilibrium, you reduce the control parameter. So it has some advantages. Can find global minima if you're given sufficient time. It's well suited for detailed placement. Disadvantages, as I said before, it's slow. A fair bit of parameter tuning is necessary, and this other point is probably not accurate. It sort of says randomized chaotic algorithms. Small changes in the input lead to large changes in the output. Probably not so much the case for these placement type algorithms. You'll end up with a different solution, but it'll be, in general, they'll all be statistically equivalent. Practical applications of simulated annealing, sort of said small placement instances, and certainly FPGA layout where they had complicated constraints. And it's break time.